This problem we're going to recover some material that we've already done so far, in particular doing a t-test on the slope of the regression, and then we're going to do some new material which involves interval estimation of the y variable. So let's look at this problem and see what we need to do to get it started, and then before we get to part B we're going to have to introduce that new material so that we can do that part. Alright, a real estate developer wants to investigate the relationship between office rents, which they're going to call R here, and office vacancy rates V. The following information comes from a sample of similarly sized cities. So we have N is 10 and sigma V is 66, etc. We're given that V is equal to 16.71 minus 2.714 times R, and below that we're given that the standard error is 0.596. Alright, and let's look at part A since we can do that already. Let's do the t-test on the slope of the regression the easiest way we can. Well, we're going to do it a way. It may not be the easiest way. Alright, so what we're going to have to do first is determine which is the x and which is the y. Alright, in general, y hat is equal to beta hat 0 plus beta hat 1 times x. Alright, so that will be our information. So let's write that down. Alright, so we have that V is equal to 16.71 minus 2.714 times R, and below that we're given the standard error. This is a typical way of writing down the standard error if it's given to us, 0.596. Alright, remember that in general y hat is equal to beta hat 0 plus beta hat 1 times x. Okay, so the V is the y variable. The 16.71 is the beta hat 0, the intercept. The negative 0.2714 is the beta hat 1. And finally that R is the x variable. Okay, and we also have that the standard error is 0.596, and the notation for the standard error is S beta hat 1. Alright, so we can write that down. What little we have there, we can write that beta hat 0 is 16.71, that beta hat 1 is negative 2.714, and S beta hat 1 is 0.596. What we also need to do now is to rewrite the sigma B's and sigma R's from here and translate those into X's and Y's. So first thing that was on that line is that N is 10 data points. Alright, sigma V is 66. That means that sigma Y is 66. Next says that sigma R is 37.25. That means that sigma X is 37.25. Next, that sigma V squared is 514. That's sigma Y squared is 514. Sigma VR is 225. That's sigma YX, or sigma XY is 225. And finally that sigma R squared is 146.4375. That's sigma X squared is 146.4375. Alright, so now we have all the data in the notation that we need to do our calculations. Alright, so first we're going to do the t-test on the slope. Before we're going to do anything, we're going to get all the sum of squares information. So first, x bar, sigma x divided by n. Sigma x is the 37.25 divided by a sample size of 10, and that's 3.725. Next, y bar, sigma y divided by n, and sigma y 66 divided by the n of 10, and that's 6.6. Next, sum squares of x, s of xx, sigma x squared minus n times x bar squared, the result of which must be positive, and it's sort of useless to us if it's 0. Alright, sigma x squared from over here is 146.4375 minus the n of 10 times the x bar 3.725 squared, and the result from that is 7.681. Next, let's do the sum squares of xy, which is sigma xy minus n times x bar y bar. This could be either, in general, positive or negative. But in this case, we're already told what beta hat 1 is, and beta hat 1 is negative. So the sum of squares of xy has the same sign, and it'll also be negative. Okay, we can use that to check ourselves, but in this case where we have a beta hat 1 given to us. So sigma xy 225 minus n is 10 times x bar 3.725 times y bar 6.6, and that's a negative 20.85. Now we can do the sum of squares of y, syy, sigma y squared minus n times y bar squared, sigma y squared is 514 minus the n of 10 times y bar 6.6 squared, and the result from that is 78.4. Okay, notice in general that sum squares of y must also be positive. Alright, so now we have all our sum of squares.